Welcome to the lecture Cryptography. Today we continue with zero-knowledge proofs and want to investigate what can we prove with zero-knowledge proofs. And so let's repeat some things. So we're looking at interactive proof systems where we have some kind of prover who knows a secret or a witness is a witness of a secret. That's terms which are used. And so we have a prover, we have a verifier, and the goal is that prover wants to verify that he knows the secret, but without revealing it. Secret should be secret after that, but the verifier should be convinced that this is correct somehow. And sometimes we can prove it with complete certainty or nearly complete certainty. Sometimes we have only a small probability, so there are different kinds of zero-knowledge proofs, but you have to look. And usually what happens is we have these so-called moves where we receive a message, and when we compute something and we send a message, and this goes back and forth. So that is a usual thing. And both parties need to be computing. Okay, I have to make precautions here again. Okay, both parties need to be computing, and one party proves and one other party verifies. Okay, now this idea is that one thing is that completeness, that the prover knows the secret and the verifier will accept the prover's proof. And soundness means that we can also convince the verifier a reasonable probability such that the verifier is convinced that the prover knows the secret. And there are two ways to attack it. One is from the prover side. So the prover just can pretend to know something and convince the verifier that this is okay. Like, do you know PowerPoint karaoke? No? Yeah, he knows. Okay. The PowerPoint karaoke is that somebody is standing in front of an audience with some slides, making a presentation, a talk, a lecture, whatever, and doesn't have any clue what it is about, but just pretends to know everything. That's called PowerPoint karaoke. And that's a dishonest prover. You know, if you think that you're sitting in a lecture and you think that the professor knows what he's talking about, it could be that he just reads the slides and improvises something, and you think that he knows everything, which is not the case because he's just pretending. So that's a dishonest prover. Now, a cheating verifier is on the other side, if you see it from the student side, is that you're sitting here in the lecture and you're trying to get the exam questions. Yeah, so maybe I just have it here somewhere on my desk and you steal it and you copy it and give it to your friends and then you participate in the exam. True story, but that's enough story. So that's a dishonest verifier. So we both actually, this lecture is some kind of zero-knowledge proof. You know? So that you go to the lecture, you're convinced that I know something, but you haven't learned anything after that. So that's a zero-knowledge proof. Okay, so that's what we have started is we started with zero-knowledge proofs that the Fiyad-Shammi identification that somebody knows a square root. So, and by this we had this protocol where we know the square root and we send another number squared, a, and then here we have one bit e in order to check whether this is correct, and then we have b, which doesn't give any knowledge, which we prove by looking at the verifier, and the verifier. So we had this notion of transcripts, where we looked at the transcript, which is a communication protocol from the left side to the right side. And if we can reproduce this transcript without the prover, just by using the verify, because the verify doesn't know the secret, then we can prove that this is truly zero knowledge. And this could be also, we are also allowed to use a dishonest verifier, a verifier which doesn't do what it's supposed to do, ask funny questions or send strange things. And this is called perfect zero knowledge if we have a probabilistic simulator for that. And we have done this for Fuyachami identification. So we have done this transcript simulator here. And what we do in the transcript simulator is basically we are choosing the things in the correct, not in the correct order. So we start with B, and then we choose E, and then we choose B, although the protocol says A, B in this order, first, second, third. We start with the last one and compute backwards. When we ask a verifier what he would have done, and if verifier would have done something different, we just start all over and try again. And since the verifier has a 50-50 chance to do something, we guess the verifier's choice with an expected number of 2 rounds. And this works fine. And since we have a transcript simulation, we don't learn anything from that. Although the verifier is convinced with probably 1/2 that is really the true story. And this was the perfect zero knowledge. It turns out that very often we cannot do perfect zero knowledge, but we have some weaker notions. One is being statistically close, and another one is so that we cannot really simulate the distribution, but only simulate with very small statistical error. Or the other thing which we will look in today is computational zero knowledge. So that means the transcript is not random, but it looks random. And looks random means that unless you can do some impossible or nearly impossible computational task, you cannot distinguish it from a random string. We also looked into honest verifier perfect zero knowledge, that we define the verifier have to be honest to do something, which plays a major role today, where we also look into a zero knowledge proof, which is computational zero knowledge and uses an honest verifier in order to get out, to remove interaction. Okay, so that was repetition. Another thing that we found out is that we so we had this exercise where we found out that we can check for square roots modulo prime number. And if you can check for square roots, that means, first of all, a generator in a field is then a non-square root. And then you can check for whether the exponent is even or odd. So this gives you 1 bit of information leakage. And we can work around this by using special prime numbers, which are in the form 2k q plus 1. In this way, p minus 1. And we don't use a generator, but we use generators which are used in this smaller group of g to the q, gk, gq. And these new generators in brackets are basically all squares, and there's no leakage there. And we are computing a modulo prime number as well. So these are 2 things which makes much easier. We will look into this in the next exercise on Thursday, when we try to find out how hard it is to find such numbers. So because we know there are infinitely many numbers, but what we don't know is that if you start with a prime number q, do we get a prime number p? Very easily. How long does it take? How often do we have to? Is it sometimes possible that we don't get any for some prime numbers? Now, these are all mathematical questions which the community cannot answer right now, but the least we can do is we can do some practical tests and turn some simulations and watch funny algorithms do something. That's what we do on first day. Okay, so going back, basically what does change? Nothing changes, because we still will look up g to the e, and we still use the discrete logarithm assumption that if we get some a, then it's hard to compute the exponent to some generator, which on the positive side now in the exponent loops through a prime number, and on the basis also loops through another prime number. So we have two prime numbers, and prime numbers are cool because they are you can compute the inverse. For every number except 0, you can compute inverse, and so this is very nice. Okay, we will have to look into this too today. So now, for the new stuff. Now we have seen that we can prove that we know the square root of something, but I don't think that you're big fans of square roots right now. Let's compute the logarithm. Or not compute it, but prove that you know it. So now what we have is we have a large prime number and we have a generator, but now for this q, because p is 2 times q plus 1. So the goal of a prover is he wants to prove that that he knows that y is a form g to the x. Of course, the prover could give g, could give y, could give x and p to the verifier, and the verifier uses iterative squaring and just calculates this equation. But then the secret is gone, of course. So we have to do something else. So the prover starts here, has some secret x, and what we do is we first take some completely different random exponent and send a to the other side. Okay? Now the verifier chooses a bit e, and now what we do is we compute the exponent, but the exponent will be either r or it will be r plus x. So here we send b. So in b is either r, which is for e is equal to 0, or it will be r plus x if e is equal to 1. So what does it mean? So if e is equal to 0, I give you a fancy random number for which I know that g to the r is equal to a. So it doesn't give you anything. Now you don't know what this means. Yeah? So that's the first case. Now in the second case, you still get a fancy random number, but you cannot compute a out of this, and you cannot compute y out of this. You just can say that this must be the exponent of a times y. So because g to the r plus x is a times y. So what we give away is that for some number, r plus x is the logarithm. For which number? Well, for a completely random number, because we have chosen r to be random. So that means that this will be a random number, and this exponent will be a random number as well. So for some random number, I give you the logarithm, which is no secret somehow, because if you go the other way, you start with the exponent, and you do g to the x, you get a random number too. So from all the possibilities that you have, you gain nothing. Yeah, so you neither get something from a first case, which is very clear, because from a totally independent random number, I compute g to the r. And for the second case, it also doesn't give you anything. But of course, you know everything if you have both, because when you just take, say, r plus x minus r, and you get x. Okay, so that's thing, and this is a perfect zero-knowledge interactive proof system that Peggy knows the logarithm of that. So Peggy does not solve this problem, of course, because Peggy starts with X and computes Y out of that. But now Peggy can convince Vic that she knows the logarithm. And by the protocol, it's complete. For soundness, let's assume that we have a cheating prover, Eve. And this, you have a chance to cheat. So what you can do is you choose a random element, B, and then you compute this formula here. So you guess what the other party would do, and either you would compute Y. So you have either, let's say, A is equal, either you send G to the B, or you send G to the B divided by Y. Of course, you don't know what the verifier will do, because you have to send your commitment A before AE is chosen, but I can make a guess. So, and if E is equal to 0, I send this, and if E is equal to 1, I send this, if I guess it like that. So that's why I have this tilde over there. I'm just guessing what could be. And if I guess correctly, then A has this property that you need. So you guessed correctly and you get through. So Eve succeeds with only probably 1/2. And how to make Eve succeed with smaller probability? Well, you do more loops of that. So if again, you could take this algorithm and you just make a huge loop here out of this. Here, say loop T times. And then Eve can cheat in every round with probably 1/2. And this is independent because you choose independent errors, and at some point Eve will guess wrong. So, and cannot cheat in this way. Because if Eve wants to be 100% sure that it works, Eve needs B0 and B1 with 2 possibilities, and B0 and B1. So this would be B0. So this would be B0, and this would be B1. And you can compute B1 minus B0, and you have X. And but then Eve is not cheating because Eve knows X. If you know X, you're not cheating. Yeah, that's the whole point of not knowing X in order to cheat. If you know it and you can use it, then it doesn't help you. Okay. So soundness works. We can convince that we know it with probably 1/2. The only way to sneak out is to guess. But if we are sure, and we can always give a correct answer when we can compute the secret. And if we can compute the secret, we know the secret as a prover. For the zero knowledge property that the verifier doesn't know anything, we can make a simulator again, which is basically the same construction that we have seen before. So again, what we have here, we have A, we have here in this direction, we have E, and in this direction, we have B. So the simulator does the following. I choose a random B. Again, we start from the from the wrong side. Because that's how you basically can simulate the protocol. Then I choose a random choice E tilde. Basically, I try to do the cheating thing. I'm simulating a cheating prover, and then I check whether the verifier would do that. Now, V star means it could be a cheating verifier. So any cheating verifier would be somebody who would try to get out this information. And in this model, I'm allowed to ask a verifier what the verifier would do, which could be different every round because the verifier could be a randomized algorithm. Okay. Now, in case I guessed correctly, I return this output. And if not, then I just do it again and ask what would the verifier would do. It's like looking into different universes and say, would you guess this way or the other way? And since the verifier has only a small number of choices, which is 2, I can try out the verifier and see whether I accidentally hit him. So since in the next round I start with a different random number, could be that the verifier would have a different answer. So it's not that's guaranteed that the next round just by inverting the result I would get the same. But here, since I have a 50% probability, then this is a Las Vegas algorithm which solves the case and simulates the communication, which proves that there is no knowledge transfer, because if you hear 2 people talking to each other and you say, this is some kind of random garbage, I can prove it because I can produce the same kind of random garbage. Then there's no information flow for you. So you don't learn anything, and the verifier also doesn't learn anything, because he could have instead of talking to the prover, he could say, I imagine that this conversation takes place and I put it in the correct order. Which is, I think, the most interesting thing about perfect zero knowledge is that on one hand we prove that there is no knowledge flow at all, and on the other side we prove that we know that the prover has a secret now. So that's mind-boggling, that's a thing. We know it because of soundness. So that's here. So the soundness is here. If we have a cheating prover, then the prover has to choose what the prover has to do. It has to, if we go back to this protocol, it has to choose A at the beginning. It doesn't know which E is coming. So that's the first thing. And then E is coming, and because if the prover has no control over E, he has to submit something like B. So you're challenging the prover. Yeah, he could actually, he has a 50% to sneak out. Yeah, so, but he cannot, what he is doing is he's actually, he has to commit to say, okay, either I prove that I know the logarithm of A, which I have sent. So actually now I'm committed to 2 things. One is A and the other one is Y. I'm giving out 2 possibilities. And now the other person can show, do you want to see X or do you want to see R? Basically, do you want to see X plus R or do you want to see X bar? But you cannot sneak out because you committed to 2 logarithms. You commit to G to the R and commit to G to the X plus R. So both of them are on the table. And there's 2 cards. And you shuffle around the cards, and now he can say, I want to see R or I want to see X plus R. But there's no way to sneak out. So that's like a card game where you have cards hidden. Okay. Yeah, and this is the easy case. So now, so this is nice, of course, that we have that we can do that, and we have a simulator and so on. But we are not very happy because we have this all interaction going on. So in order to get probability of 1/1 million cheating protocol, you have to do this 20 rounds. Can we do this in 1 round? And the answer is almost. Or yes, but that's the answer. So let's look at this protocol, which is called Schnorr's identification protocol, which is very similar to the thing that we just have seen. We still have the same goal. We still have Y. Now we do the following. We choose a random R. That's the same thing. And then we send A to the other party. Okay. So this is now the point where in the other protocol we just skid a bit. But here what we get C. Okay. So now, again, we have committed to g to the x, and we have committed to g to the r. So, but now what he's asking is, well, do you know, well, if you know the logarithm, then let's see whether you can build, instead of g, here, instead of y to the e, take y to the c. Take your secret, which is g to the x, and compute this to the power of some challenge in the exponent. Okay? And this should be something like your first submission. And in order to prove that you know this, please give me the b, which makes this equation 2 in the exponent. So again, we are somehow constrained between x and r. He challenges our g to the x to multiply with c and then compute the b with this property, which is somehow the same thing that we have done. But now, there's no easy way to sneak out of that just by guessing. Because we cannot guess what the verifier has done. So we send this b. So b is now the exponent of something, which is, if we don't know r, somehow a random number again, because a random number minus some challenge times x. So the result will be that he answers with a random number, which is somehow related to a and to y that we had in the beginning. Now the receiver checks this equality here, whether a is g to the b times y to the c, and accepts. So this is an honest zero knowledge. This is honest verifier zero knowledge proof, because we can build a simulator for an honest verifier, which is not so hard, because what we can do is we start with b, random, then we compute a, we use with b, and then we return this value, and we can check whether this is the property that we need. So again, we just flip the order by starting with a challenge, then computing and then b, and then we compute the result, and we can just check that this is 2, because now we have chosen a is g to the b times y to the c, and on the other side is of course the same, g to the b times y to the c. It is not known whether this protocol is perfect zero knowledge. Or the other way, we don't know how to show that for a cheating verifier we could build the same protocol in polynomial time. Of course, you could do and say, okay, I guess the random number from the verifier, the challenge, and if I haven't guessed correctly, then I repeat. But the disadvantage is that you have to guess q minus 1 possibilities. And this is something you cannot guess. So the algorithm that you have seen for the cheating verifier doesn't work anymore. If we have an honest verifier who chooses a random value, we can simulate it. So that means for the honest verifier, there is no information flow. So if the verifier is dishonest, we don't know. There's one way to get out some information. So that's a disadvantage. However, we are going now in a totally different direction. And this was an idea that he had in the last lecture, which, yes, you had an idea in the last lecture, so probably this is very straightforward. Here at this point. At the other point, it's harmful, but here it's straightforward. We replace the verifier with a hash function. So this is called the Fiat-Shamir heuristic, And it works for certain honest zero-knowledge proofs. Because what's the job of a verifier here? The verifier just has to pick a random number from an exponential sized space of possibilities. So what we do now is we just remove a verifier. We don't have any actions. It's like that we carve the proof into stone. There is no actor action anymore. So we choose a random R. We choose this challenge, which is A. So this commitment of A is G to the R. And then we compute the challenge. So this is replace the verifier. That's what we do. So the verifier is now a hash function, which produces a challenge. Now, it's very important that here, in this case, A is inside. So we give him A, and then he computes a challenge, and then we answer it, and then we have a signature which proves that we know the logarithm, and anybody who reads this says, okay, this is maybe not the random number I've chosen, but this is a random number that the prover has no or little control over. I say little control because the prover could do the following. The prover could do the following. The prover could try out several random choices R over and over again and see whether he somehow hits the challenge. He makes a random idea for the challenge, then takes a random number and tries it out whether it works. And again, and again, and again. Now, since this search space is exponential, it's not possible that this algorithm succeeds in polynomial time. Since now we have so many possibilities, it would work if the verifier would have a constant choice. And we say the hash function maps to a constant choice. Then we only have two tries to try out, and then it wouldn't work. But here, it's very important that this is exponentially large, and thus it's exponentially large. That's very important in order that we can apply this technique. So now the prover does all these things, and the verifier can check it later on. So verifier can check, okay, gets all the communication, checks whether the challenge was computed correctly, and checks whether this is. So what we have done now is we looked into zero-knowledge interactive proof system and removed the interactive part. So there is no interactive part mirror. So you can now prove to somebody that you know something, and he believes it because it's just in the system, like that. So which is the next mind-boggling thing that you get, but we don't stop here, of course. Now we have to discuss what the Fiat-Shamir heuristic means for these now non-interactive zero-knowledge proofs. So you can convert these public coin proofs into non-interactive proofs. And so first thing is you have to use all information for the hash function. Just think of here that you do not use A. If you don't use A, you just use R. You just choose R in such a way that it fits, and you can. That this equation is somehow. So you have a challenge now, and now you can change R that it fits to the challenge, and that's an easy task that you can compute that. So you have to put everything into the hash function, and if you don't do this, then there are certain attacks on existing protocols called frozen hard attacks and things like that, which actually are harmful and where a prover could cheat. Okay, so we need also random bits so we produce random bits and a random number from some field, and we have to make sure that this is large enough. So the motivation, of course, is that cryptographic hash functions are approximation of random numbers. And the result will be a digital signature. again. So we prove with something like a digital signature that we know something, and we can just publish in this way. Now, this emulated challenge, this emulated interaction and producing channels, the problem is that the proofer can produce many attempts a priori. So he sits down and chooses at some point in the algorithm, chooses random number and does it over and over again. So that's the critical part. So usually, if you do the Fiat-Charme heuristic, you have to set the bar for the security higher than if you have an interactive proof system. Because it could be that using this scheme, the prover produces 1 billion tries a year long how to find an example to prove that a certain thing is true. So you don't know what the prover has invested in time in order to guess it. But this is something we already know from hash functions. So hash functions are also around, and they're at this moment trying to find possible collisions, and somehow it works. So hash function must use all relevant parameters. And good thing is, an honest verifier zero knowledge suffices. So it's not necessary to have a perfect zero knowledge proof, because the hash function emulates the honest zero knowledge proof. And this is in the protocol that we see, okay, this is really done in the correct way. We check with the hash function that this is honest zero knowledge. The big bad thing is it's not provable secure. So you don't know, there's no proof, or we don't know how to prove that Fiat-Charme heuristic produces something which is reliably secure, or at least based on some kind of mathematical assumption that you have. Okay, so this, let's say this is a good point to make a break, because after the break we see tons of more zero knowledge proofs, and I prove here everything, or maybe not everything. Let's see.